practical bug detection LLM-integrated approach.
Okay. Thank you for your introduction. Hi, everyone. This is Hao Nan Li from UC Riverside. So today I'm going to share about our recent work, basically using large language model to help static analysis for bug detection in practice. And actually, this work is inspired by our experience in static analysis. We do fail for static analysis, especially when you try to use static analysis for, for bug detection in practice, you will face many real challenges. Actually, ChatGPT will also agree with us at this point. If you ask ChatGPT what kind of disadvantages of the static analysis, it will tell us the following disadvantages of the static analysis. And actually, I picked some points here to share with you guys. And the first biggest problem is false positive and negatives. And also, static analysis is also struggle with its high complexity and also scalability issue. And static analysis, many static analysis also typically has limited domain knowledge. So it motivates us to think about how to solve these challenges. And of course, just as our title indicates, our solution here is using large language model. Compared to static analysis, LLM is very smart, and it typically has lots of domain knowledge and heuristics. Sometimes you can rely on LLM to give you some smart summary for kind of complicated code structure that static analysis may struggle with. But however, on the other hand, you can see LLM is also known for its unstable response, and they are typically has limited reasonability, especially when you try to reason on the code. So the problem here is, how can we really enhance static analysis by integrating large language model? So to answer this question, we researched on a specific static analysis tool called UBI tag. The UBI tag is designed to find use-before-initialization bug or UBI bugs in the Linux kernel. And the UBI is basically saying that variables may not be initialized during their use. For example, in the right figure shows there's variable v at line 2 and declare at line 2, and then there's an initializer for the variable v at line 4, and then v is used at line 5. So you can see at the line 5, the variable v may not be initialized because there's a constraint here. So before reaching the line 5, and here v is a UBI bug. The reason why we choose UBI tag as our target is because actually UBI tag shows many disadvantages of the static analysis. For example, it's false positive and negatives and so on. UBI tag actually has two design strategies. The first stage is static analysis. It's a static analysis is scalable one, but imprecise one. And then it's followed by a symbolic execution. It is very precise, but of course it's slow. So the first problem is the false positives. Actually, their static analysis can produce more than 95% false positives. So to handle this huge amount of false positives, UBI tag choose to employ symbolic execution to filter out these false positives by verifying the path. But however, symbolic execution is not perfect. It actually causes another biggest problem, the false negative. This is because symbolic execution can actually handle 60% of cases, and it will discard 40% cases, undecided cases, because of time or memory limitation. In other words, it may ignore 40% potential bugs. Let me give you a concrete example of the undecided cases. Here is the scanf. You can see at line 2 of the code, ABCD are declared at line 2, and in line 3 and 4, if you ask human to understand, it is pretty simple and straightforward. There's a scanf. Scanf try to initialize ABCD, and more importantly, at line 4 there's a check to see whether the return value is greater or equal to 4. As we all know, this means when the scanf successfully initializes its first 4 parameters, then it will return a value greater or equal to 4. And in that sense, we can say at line 5, when ABCD be used, it is pretty safe. It is pretty safe. All the variables of ABCD are already successfully initialized. But however, this is very straightforward and easy for human, but this is not as easy for the static analysis. Our static analysis is essentially path insensitive, so it can only tell us scanf may not initialize by scanf, and it will report a UBI bug at line 5. And later, UBI tag will send this case to simplification. But however, when simplification goes into the details of the definition of the scanf, it will say when it wanna infer the return value, it will say there's a variable num, and the num is essentially accumulated by the loop. So simplification cannot really handle this case and ends up a timeout. So the only thing UBI tag will do is to directly discard this case. Of course, so this case scanf is clearly a false positive. The right thing you should do is discarding it. But actually, this strategy of the UBI tag directly discarding timeout cases will, is essentially, we will essentially have a risk of reject genuine bugs. So again, just as I mentioned, this case is pretty simple and straightforward for human to understand. So of course, we try to LLM, we directly ask ChatGPT, are variables ABCD to be initialized before reaching the line 5? And actually, you can also scan this QR code to see the exact chat. And basically, ChatGPT will tell us here scanf is to is used to parse IP address, and by the time the call reaches the line 5, ABCD have been already initialized. So actually, the scanf is an example. It demonstrates that sometimes LLM can effectively analyze call logic that static analysis, our traditional static analysis, may struggle with. So based on these insights, we propose LLift using large language model to handle these challenging undecided cases. In a very high level, LLift takes these undecided cases from the UBI tag, and then we will ask LLM, are these variables initialized before they are used? And if LLM tells us must initialize, we will mark it as not a bug. Yeah, but of course, if you literally ask LLM, are these variables initialized before they are used, it won't work. This table is directly copied from our final evaluation. You can see we call this directly asking strategy a simple prompt, and you can see the simple prompt has pretty bad precision and recall compared to our final design. This is basically because bug detection. Our bug detection task is kind of complicated, and it essentially requires steps with kind of rigorous rules, just like what our static analysis do. And actually, LLM is unaware of them. So here, our solution here is actually, we don't LLM to think by itself. We will teach LLM. We will give the guidance to LLM for every steps and rules of the, of the bug detection. In other words, you can also understand it as we teach the LLM the mindset of the bug detection. But due to time limitation today, I'll show you guys all the details of our design. But I will give you some high-level design principles. I think that's the most important part of our work. And the first design principle here is, we call it is task decomposition, basically, because the bug detection is a very complicated task, so we'll break it into pieces that is more manageable for LLM to think, to respond. And the second one is, we call it post-constraint guided path analysis. This is just as this shows. There is a variable v used at line 13. Line 13 is use of v, and the most critical part here is the line 12. There is a return value of the initializer, and to say the return value if the return value equal to 0. We call this return value equal to 0. We call this check as post-constraint because it actually happens after the initializer. So we notice that we can actually take this post-constraint into analysis of our initializer from the line 2 to 7. So basically, if we already know the return value must to become to 0, because otherwise there's no use, no UBI then no UBI happens. So actually, with this constraint, we can see very clearly the code can only reach the path 1. And we can directly prune the path 2. And this way, we can reduce a lot of unnecessary paths in our analysis. And the third design principle here is, we call it progressive prompt. Basically, in one word, the progressive prompt is to let LLM itself decide what they want for function definitions. And you can see the whole process is iterative. LLM can continuously ask for different function definitions until it feels it has enough information to give a conclusion for the function summary. So our workflow can be seen as a 3-step design. The first, we will take the bug report of the UB attack and identify what is the initializer. And for example, in this case, the initializer for sure is scanf. And then we will extract the post-constraint. And here, the post-constraint is return value greater or equal to 4. And lastly, we will prompt LLM to analyze the initializer with our post-constraint guidance. So let's talk about our evaluation. Actually, we have 4 research questions in our paper, but today, again, due to the time limitation, I will focus on the first 2 parts of our evaluation. The first is precision and recall, and the second is some interesting result on other models than GPT-4. And our primary data set is, we call it random 300. Basically, it is coming from 300 cases from 53,000 undecided cases of UB attack. And for the precision, the line, above the bottom line is coming from the random 300. We actually have 5 true positives with 50% precision. And for the recall, we don't really find any missed bugs in the random 300 cases. And furthermore, we also extend 300 to 1,000 to try to find more true positive bugs, and we do find 13. In total, 13 true positives and also 13 false positives. So again, the precision is still 50%. And actually, 4 of them are already confirmed as real bugs by the Linux community. And also, there are some interesting results. It's coming from for other models than GPT-4. A big disclaimer here is that actually this table is not coming from our paper. It's actually extended work after the paper submission. So you can see LLift, our work can still perform very good on most other models. More interestingly is that even for open source models, for Llama, they still show a very useful and promising result, but just there are 2 negatives, or in other words, they have a much higher false positives. I'm super fast. So in summary, we present LLift today. It's the first work to show how to use LLM to improve static analysis in practice. And secondly, LLift also introduces some new design strategies, post-constraint guided path analysis and the progressive prompt. We believe this kind of design strategies can also help future studies in this area. And lastly, we test LLift on real-world codebases, and we also achieve a very good precision and recall, and we also find 13 new true positives. And by the way, I will have a poster later today, and welcome to discuss with me later, and also you are welcome to give me some questions. Yeah, thank you for listening.
We have time for a few questions. Can you come up to the microphone, please?
Hello, thanks for the great talk. I have maybe a silly question, but I'm just wondering, so you wrote some rules in the prompts. I'm just wondering, couldn't you synthesize those rules in the static analysis part to improve the accuracy of that?
You mean use these rules in a traditional static analysis?
Yeah.
For example, yeah. For example, for our post-constraint guided path analysis design, literally you can also design in a static analysis way. Yeah, of course you can. And I believe if you really implement it with kind of a much more complicated work, you can also see the improvement.
Very nice talk. I'm Chen-Peng Wang from Purdue University, and we also work on the similar directions as yours. I think the interaction between the symbolic analysis and the LLM is very interesting. But my current concern is that whether the performance of your evaluation actually depends on the precision of the symbolic analysis. For example, if many false positives are caused by the path insensitivity, and according to my experience, LLM cannot really filter such spurious paths just by reasoning the path condition without using any kind of solver.
Actually, I feel like actually, you can see just this slide. Oops. Yeah, these slides, our post-constraint guided path analysis. We do feel like for many cases in practice in the Linux kernel, we don't have a formal solver for the constraint for the post-constraint, but actually for most times, for this kind of return value, or you can say return value check. This kind of return value typically they will return an integer or return an error code in the Linux kernel. So in this case, it's quite simple to infer and the prune path.
So basically, the original symbolic analysis can really report this bug, right, as a false positive, and LLM can filter it.
Yeah, if this case is really as simple as this form, but again, for many more complicated code, just as the scanf case, simplification can do nothing with it.
Okay, because according to my experience, I do some experiment upon Julia test, even in some simple programs such as Julia test. If we detect divide by 0 or non-pointer dereference, the branch condition can be equal to 0 or not equal to 0, equal to null, not equal to null. I think the LLM alone will hallucinate when you just give the branch condition. So basically, I think the future extension could be ask the model to synthesize some script program and just find such on-site call.
Yes,
I think it can mitigate some hallucination in this process.
Yes, for sure. But all the design is based on is essentially inspired by our experience. In our case, in our scenario, we don't really meet so many like complicated constraint like what you're saying. But I also agree with that is definitely necessary if you want to figure out something like divided by 0 or non-pointer dereference. Yeah.
Okay. Thank you for your answer.
Okay, let's thank the speaker again.
Okay, thank you.